I hope everyone's doing well. I'm Mr. H. Thank you for joining me for this basic video here on basic organometallic reactions. What does it mean, organometallic? Well, you know the organic means a carbon atom and metallic means it's bonded to a metal atom, and there's something else going on over here, but you have in essence a carbon metal bond. It's special because it will be a polarized bond, because this is electropositive and compared to that this is electronegative. You'll have a partial negative here and a partial positive character. It'll be a polarized bond. You can view it if you were to separate it as this: C minus and M positive, metal positive, carbon minus. In terms of charge separation, this is what you have. Then this item right over here can act as a nucleophile. The purpose of this type of reaction is to create carbon-carbon bonds. You're trying to create carbon-carbon and then you're propagating a small molecule and making it larger, and you can end up forming alcohols as well. So let's look at a good representative reaction. Your best means for using an organometallic reaction is with a carbonyl functional group. Here you have your carbon metal bond. You know, I've told you this is partial negative, this here is partial positive. But when you're comparing carbon and oxygen, this is electronegative due to a dipole moment. This right here is partial negative, this right here is partial positive. And you know, opposite charges attract. This right here, this carbon is negatively charged, is going to behave like a nucleophile. This here is partially starved of charge, is positive. So you can have a nucleophilic attack over here. And then this negative oxygen, which has two lone pair of electrons, 4 of these lone electrons, it can come and attack the metal. You have this bit of reaction going on behind the scenes, and it helps you generate what will be a carbon-carbon bond. You see this carbon, it will add over here. You will have this carbon come over here. This is the carbon which you see over here. This oxygen is going to now become associated by means of a interaction with the metal, and then something else can go on and you can get rid of that aspect on the top, or you can retain it and convert it into an alcohol. But what are we looking at here? A carbon-carbon bond has formed. You didn't have a carbon-carbon bond here, but now you've added it here by means of an organometallic process. Let's look at it with an actual example. Let's look at a reaction. We're starting here with cyclohexane. You know the valence of each of these carbons is 4, so you're really looking at cyclohexane, and each of these will have 2 hydrogens all around. There are 2 hydrogens everywhere. Anyhow, we're looking at it in terms of your diatomic bromine in the presence of ionizing radiation. Keep in mind there are hydrogens involved. I'm not showing them, but they are involved. In the presence of this ionizing radiation, the bromine, diatomic bromine, will separate into 2 bromine radicals. As you can see, the bond will separate, one in this direction and one in this direction. You'll have your 2 bromine radicals. One of those bromine radicals will attack the cyclohexane ring. You know there are 2 hydrogens over here. One radical will attack a hydrogen and one will attack your ring. What will you get? You'll get cyclohexyl bromide plus HBr, because you know there are 2 radicals generated. One is going with the H, one is going with the ring. So we've generated the cyclohexyl bromide. This is what I'm interested in. What I'm going to do is attack this with magnesium. It's going to be my metal. The organometallic reagent will develop. When we do this, now what are we generating? Cyclohexyl magnesium bromide. That right there is my organometallic reagent. But what is it specifically? It's called your Grignard reagent. That's what it is, Grignard reagent. This reagent, named after the person who invented it, is used for creating carbon-carbon bonds and alcohols. This Grignard reagent, now MgBr attached to your cyclohexane, can be attacked. You can either attack it to, let's say, formaldehyde, or you can attack it to acetaldehyde, or you can attack it to other items which have a carbonyl group, and you can even attack it to acetone, CH3 cetyl bond O CH3. You know you have aldehyde, and you have a ketone, but your end results will be varied with regards to what you're using. The Grignard reagent, you would be doing all of this in the presence of either ether reagent or tetrahydrofuran. That would be your solution in which you're doing it, in ether and tetrahydrofuran, followed by H plus and water. I'm not going to show it to you, but you can say that in the presence of ether and tetrahydrofuran solution, and followed by acid hydrolysis, because that acid hydrolysis will get rid of your metal at the end and take it away. These are 3 independent reactions we're doing, and each will yield a different type of alcohol. In a stepwise manner, let's look at each of these. When I'm looking at this Grignard reagent, cyclohexyl magnesium bromide, and I'm attacking with formaldehyde, what am I getting? This is what I'll have. I have my cyclohexane ring, which is like this. I'll have CH2 and OH. Here I've developed my carbon-carbon bond. Remember, the basic premise is to develop a carbon-carbon bond, and this is what I have. What's my my byproduct, MgBrOH. Why? Because I'm doing everything in the presence of ether or tetrahydrofuran followed by acid hydrolysis, H2O in the presence of acid. That's where you're getting that OH. So this is my product for reaction A. Cyclohexyl magnesium bromide, my Grignard reagent, in the presence of formaldehyde will give me this primary alcohol, because you have an alcohol group attached to the primary carbon. Where is this OH coming from? It's coming from your carbonyl group. So this is the end result of reaction A. Let's look at the reaction B, and we look at everything, then we'll be done. You'll always have that byproduct, as I'm going to show you with each reaction. When you're looking at B, we're going to have this as our end result. It'll be a secondary alcohol. I have a CHOH and a CH3 plus MgBrOH. This is a secondary alcohol because this carbon, which is holding the hydroxyl group, has one carbon here and one carbon here with your cyclohexane ring. So this right here is secondary alcohol. This is coming from reaction B. My Grignard reagent reacting with acetaldehyde will give me a secondary alcohol. Let's look at the last one, reaction C, with acetone, and you can imagine that to be a tertiary alcohol, and then we'll be done. When you're looking at reaction number C, you have this as your end result. You have your cyclohexane here, you have a hydroxyl group, you'll have one methyl here, one methyl here. This is your one methyl, this is your one methyl. This carbonyl group is giving you this with the alcohol. So here's your tertiary alcohol. This carbon is attached to a hydroxyl, but this carbon, and this carbon, so it's a tertiary alcohol. So keep in mind, when you have a Grignard reagent, you're attacking with formaldehyde, you have a primary alcohol. When you're reacting it with something like this in acetaldehyde, you'll have a secondary alcohol. With something like this, you'll have a tertiary alcohol. But in all instances, you're developing always a carbon-carbon bond and an alcohol along with this. But this alcohol can be removed by further steps, and you have indeed developed a carbon-carbon bond. Your basic organometallic reaction, which is using the polarity of a carbon and metal bond as a nucleophile against a carbonyl group, the carbon of that carbonyl which is electrophilic and partially positive, your basic premise is to develop carbon-carbon bonds and alcohols, but the alcohols can be removed away and you're always left with that carbon-carbon bond. And you can propagate a small molecule and make it larger. And that's it for this video. Thank you.